A major hurdle in crafting a space station lies in the limitations imposed by the size of rocket fairings, even with advancements in rocket technology. These fairings restrict the size of modules that can be launched. To tackle this, Sierra Space has been developing inflatable modules. These modules are launched at a manageable size and then inflated in orbit. Recently, they achieved a milestone by successfully conducting a crucial test, subjecting a full-scale life module to an ultimate burst pressure test, UBP. This test marks a significant advancement in their efforts. It represents one of the last steps before these test units are sent to space for actual orbital testing. So, what happened during this historic test? Are we one step closer to having inflatable space stations? Let's find out. Sierra Space has been diligently testing its large integrated flexible environment, life module, through various methods over the years. Initially, smaller-scale test articles underwent the ultimate burst pressure, UBP, test to ensure design safety. This involved incrementally increasing pressure until the habitat reached its breaking point, providing crucial strength and durability data. Additional tests included subjecting the pressure shell to extended periods of pressurization in long-duration tests. These milestones were achieved on smaller test articles until recently. Just a few days ago, Sierra Space announced a significant achievement via Twitter, marking a major milestone in the development of the first commercial space station. They successfully conducted the first UBP test on a full-scale life structure at NASA's Marshall Space Flight Center. The results exceeded NASA's recommended safety levels by 27%, reaching 77 psi before bursting. NASA's safety standard is set at 60.8 psi, calculated by multiplying the maximum operating pressure of 15.2 psi by a safety factor of 4. In the video, as the pressure builds up, you can observe the fabric stretching out on the left side before the entire shell gives way and bursts due to the immense pressure. To design a structure that is both inflatable and incredibly strong, Sierra Space utilized a unique combination of materials. The primary component is the restraint layer for the life module, made of high-strength soft goods materials such as Vectran, which are sewn and woven fabrics. These materials become rigid structures when pressurized. It's noted that under normal operating pressure, the Vectran soft goods materials become 5 times stronger than steel, exceeding safety factors for the station's lifetime performance. Complementing the restraint layer is a bladder, allowing controlled inflation and pressurization up to the ultimate burst pressure test failure. Together, these elements create a structure robust enough to withstand impacts from micrometeoroids and other projectiles. This specific test focused on the life habitat's pressure shell, or the restraint layer. Before this full-scale test, Sierra Space collaborated with its soft goods technology partner, ILC Dover, to design and test Vectran straps at the component and subscale levels. In the future, the life habitat is planned to be compacted within a standard 5M rocket fairing, and then inflated to the size of a 3-story apartment building once in orbit. Sierra Space envisions that, with just 3 launches, the modular life units could establish a living and working space in space that surpasses the International Space Station in terms of volume. Looking ahead, the company aims to refine its designs further. For instance, a version with over 1,400 cubic meters of space, packaged inside a 7-meter rocket fairing, would exceed the size of the ISS in a single launch. Essentially, assuming the initial life module operates as intended, Sierra Space plans to continue iterating and expanding its size. With the completion of this test, the focus shifts to what lies ahead for the company and its hardware. What are the next steps in advancing this technology? Expanding on its recent success, Sierra Space has announced plans for an ambitious testing campaign throughout 2024. This campaign will encompass tests at both sub and full scales, including a series of ultimate burst pressure (UBP) tests. Concurrently, they will begin early-stage development of the primary atmospheric barrier and micrometeoroid orbital debris (MMOD) layers. These developments are set to unfold in the coming months, promising exciting progress in space technology. Presently, several ambitious plans are already in motion for these modules. One of the most prominent projects is the Orbital Reef, a commercial space station jointly led by Blue Origin and Sierra Space. Within the scope of this station, Sierra Space is anticipated to contribute multiple life modules, likely constituting the bulk of the station's pressurized volume. Recently, there was some confusion regarding the future of Orbital Reef and the partnership between Sierra Space and Blue Origin. However, the two companies have since clarified their commitment to the project and reaffirmed their partnership. In practice, they envision utilizing the New Glenn rocket to transport both the main hard structure modules and the uninflated life habitats to space. Over time, these modules would be connected and inflated, gradually forming the Orbital Reef Station. Despite the recent successful test, the operational launch of Orbital Reef is not expected until later in this decade. This delay is attributed to plans for life modules to significantly increase in size over time. The Life 1.0 model currently offers a volume of 285 cubic meters, while the upcoming 2.0 model will provide 600 cubic meters. The 3.0 variant is projected to boast an impressive volume of 1,440 cubic meters. Sierra Space emphasizes that this increased volume in the 3.0 variant will enable enhanced crew capabilities, volume allocations, and layout adjustments. The standard life habitat is designed to support 4 crew members for long-duration missions such as those to Mars. However, Sierra Space notes that it comfortably accommodates 6 crew members for missions in low Earth orbit (LEO), and can temporarily house up to 12 crew members during transition periods. Due to its modular design, additional habitats can be connected to accommodate more crew members or serve various other purposes. The only non-inflatable component is a vestibule, which serves as the main solid component to connect the segments and provide entry and exit points into the habitat. Sierra Space believes that one of the most remarkable aspects of the life habitat is its adaptability to accommodate a variety of businesses, ranging from in-space semiconductor manufacturing to pharmaceutical microgravity research. Leveraging the unique conditions of zero gravity, the habitat provides an optimal environment for experiments and processes that benefit from this distinct microgravity setting. With substantial volume, power, and data capabilities, Sierra Space is confident that the habitat is well suited for extended human habitation, both for missions in lower orbit and for the demanding challenges of long-duration voyages such as lunar and Mars surface habitation. Years ago, Sierra Space set up a full-size mock-up of the habitat, complete with interior furnishings and various equipment typical of an actual mission. In an image depicting the second floor, a crew work area with computers and shelving can be observed, with the floor and ceiling likely secured in place using sectional pieces for assembly in space. While the main habitat is inflatable, most of the equipment inside it is not. This necessitates the use of space-efficient pieces of equipment and necessary structures to fill the space. Another image showcases the company's Astro Garden near the access hatch. Moving up to the third floor, a look at the crew living area and galley table reveals the impressive space available. Once in space, all the air and water required for survival would be delivered by logistics carriers to the habitat, where it is then stored until needed. The life habitat is equipped with life support systems that play a crucial role in regulating the air to maintain optimal conditions, including proper pressure, temperature, humidity, and oxygen levels. These systems are designed to recycle a portion of the air and water used, thereby reducing the amount that needs to be continuously delivered to the habitat. Remarkably, in terms of size, the life habitat is designed to be compatible with the Space Launch System (SLS) rocket. This is because it expands only after reaching orbit, making it more manageable and cost-effective to transport. This innovative design approach simplifies the logistics of launching the habitat into space. That's all we have for you today. If you want us to continue following the development of this revolutionary space station, please let us know in the comments below. If you liked the video, remember to leave a like and subscribe for more videos on the latest in the world of space exploration.